flight. Ever since the Wright brothers first took to the skies in their home-built aircraft, we have been pursuing more and more advanced innovations regarding heavier-than-air aviation. One of the latest technologies to emerge from this pursuit of dominance in the skies are drones or unmanned aerial vehicles. But what is the future of this engaging field in aerospace technologies? From thousands of different possibilities, our team from the Civil Air Patrol Coastal Charleston Composite Squadron believes the answer is remote 3D mapping and the different opportunities this advancement could bring. In this video, we intend to cover the benefits of UAV 3D mapping versus traditional surveying methods, the different instruments needed to perform the accurate scanning, and alternative technologies to accommodate drones, the logistical aspects of handling and operating such a drone, and finally, different applications in modern circumstances for this technology. To begin, let us consider the question of why we think this emerging field of remote 3D mapping is the future of drone technology. Simply put, not only is it a significant edge over traditional surveying methods, but it is an advantage for both the public and private sector, including the military. Remote mobile UAVs offer serious advantages in numerous categories over traditional surveying methods, such as real-time kinematics, known as RTK, positioning and satellite navigation or handheld devices. In recent studies, UAVs require only 3% of conventional RTK GPS-based data acquisition time and were able to always record the entire survey area. Furthermore, in coverage, UAVs are able to require 3D orthophoto displays, a measurement consistent representation of three-dimensional data, which can be very helpful for field engineers for the direct measurement of distances, areas, and positions, in particular when creating cross-section views or other terrain map information. Unfortunately, RTK GPS, or conventional surveying approaches, are simply not effective or accessible enough to gather this data. Obstacles can be maneuvered around and the data obtained from different angles using UAV technology. These options are simply not available to satellite-based methods. Finally, when considering safety, UAVs are able to access locations that would otherwise be dangerous to ground-based operations. All these are significant advantages over current technologies and open up endless possibilities for the applications in modern circumstances that we will discuss later in this video. First, we have to discuss the mapping technology. Of course, to successfully transition into drone-based photogrammetry, suitable technology needs to be available to complete the 3D surveying, namely synthetic aperture radar, or SAR. SAR is a form of radar scanning that is used to create three-dimensional reconstructions of objects, such as landscapes, by utilizing the motion of the radar antenna over a target region to provide finer spatial resolution than conventional beam scanning. They are capable of high-resolution remote sensing, independent of flight altitude and of weather, as they can select frequencies to avoid weather calls signals. Unfortunately, while these systems have yielded high-resolution images, SAR hardware suffers from increased weight, substantial power consumption, and high costs. Considering these disadvantages are particularly limited in airborne systems, a low-cost, power-saving alternative would be a valuable enhancement. Enter the dynamic metasurface antenna. A recently released SAR added a dynamic mesoface to the antenna, which makes it more flexible, more efficient, and cheaper than anything built before, while maintaining the same image quality as traditional synthetic aperture radar systems. That gives them a wide range of impressive abilities. The flexibility offered by dynamic mesofaces can be used to steer directed beams for enhanced signal strength. create nulls in the patterns to avoid jamming, probe a large region of interest with a wide beam, or even interrogate multiple positions at once with a collection of beams. This new advancement in SAR technology is a large benefit to unmanned aerial vehicles for 3D mapping. Having better, high-resolution imaging techniques is obviously useful, but the biggest advantage is the cost. Dynamic mesofaces can be printed in low masses at low cost. This would make the mass production of UAVs in this nature not only fit size and weight requirements, but also significantly reduce expenses. With the matter of actual scanning technologies discussed, this brings us to the topic of logistical aspects of building, handling, and maintaining such a device. With recent advancements in scanning technologies, such as with the dynamic mesoface antennas discussed earlier, size and weight of the needed equipment are at appropriate levels to be handled by UAVs, while maintaining resolution and clarity. When considering frequency bands, the SAR equipment and the UAVs will most likely use different bands depending on the situation, but will most likely stay between 1 and 8 GHz for most surveying missions. Finally, when actively using SAR, the operator should maintain appropriate distances away from the drone, or use appropriate shielding, and should always be aware of other personnel around them. Utilizing this SAR technology has a wide span of applications in remote sensing and mapping of surfaces of the Earth. Applications of SAR include topography, oceanography, glaciarography, geology, and forestry, including forest height, biomass, and deforestation. Volcanoes and earthquake monitoring are also possible through SAR technologies. They can be applied for monitoring civil infrastructure stability, such as bridges, and are useful for environmental monitoring, such as oil spills, flooding, urban growth, global change, and military surveillance, including strategic policy and tactical assessments. A drone equipped with SAR could be programmed to fly and scan the same route over and over again. This would allow environmental groups, government agencies, or private companies to scan and monitor the changes of a specific area over a long period of time in many different topics, including topography, forestry, and terrain discrimination information, as mentioned earlier. Examples on how this type of orb would come in helpful have arisen from recent unfortunate events. One such event was the recent explosion in Beirut. A flying orb with scanning equipment could become extremely essential to emergency personnel by being able to penetrate inside areas that are still unsafe to humans. Unfortunately, no such equipment was on hand after the explosions in Beirut, and the investigation required more time for teams to slowly search the area than it would have been for a drone to quickly scan the land. In such a situation, every second wasted is possibly a human life lost for being trapped within a dangerous explosion area. Aerospace technologies have come a long way since the Wright brothers first took flight on December of 1903. These advancements in UAV technology will change the way we do 3D mapping and scans. No longer will teams of people spend countless hours in dangerous areas mapping terrain from the ground. Dynamic mesoface synthetic aperture radar on a small drone will replace that. Synthetic aperture radar on a drone can scan through smoke and clouds in a much faster, safer, and accurate manner than teams on the ground. This is the future of 3D mapping.